Hello everybody, my name is Jacob Mower, and today we are going to be talking about resistors in parallel and in series. First, we will talk about what a resistor is. Then we will talk about what it means for a resistor to be in series, and then what it means for a resistor to be in parallel. Then we will talk about a concept entitled effective resistance. Lastly, we will finish by learning how to simplify a complicated circuit using the principles we will learn in this lecture. Okay, before we talk about resistors in parallel and in series, I think it would be important to discuss what a resistor is. Resistors are objects that reduce or restrict the flow of current through a circuit. Usually they convert electrical energy into some other type of energy, such as heat or light. The resistance is measured in ohms and represented by the symbol omega, and in a circuit diagram, a resistor looks like a zigzag line like this one seen here. Resistors are super important. If we remember, they convert electrical energy into heat or light, we can start to see just how useful they can be. Most of the lights in our homes are just glorified resistors. Toasters, electric stoves, and heating units are all other applications of resistors. We need to remember, though, that current only flows through the circuit in one direction. It is like water flowing through a pipe. If we think about current as water flowing through a pipe, then a resistor would be a reduction in the diameter of that pipe. This is really important, as we'll see soon. Also, with this little illustration, we can see how current flows through the circuit from the positive terminal of the battery all the way through the first resistor, the second and third resistors, until finally it returns at the negative terminal of the battery. Okay, now we're ready to start talking about resistors in series and in parallel. We're going to start with resistors in series. Resistors in series are resistors that are along the same pathway in a circuit. To be able to simplify the total resistance of all of those resistors, we simply add all of the resistances together to obtain our total resistance. The total resistance of the resistors in series is always going to be greater, since as the current flows through, it's going to hit one resistor and be limited, and then it'll hit another resistor and be limited. And that limitation will increase and reduce the total flow of the electricity through the circuit. Here's an example of a circuit with resistors in series. We'll see as we look at the positive terminal of the battery and we follow the flow of current, the current will go up and it will pass through this first resistor. And then later on in the circuit, it will pass through another resistor. That means these resistors are along the same pathway. As we keep going, we will see that the third resistor is also in the same pathway as the first two before the current eventually returns to the negative terminal of the battery. What we'll see is that all we have to do is add together R1, R2, and R3 to get the total resistance of the entire circuit. So we'll simply plug in values for R1, R2, and R3. We know that R1 equals 15 ohms. So we plug that number in for R1. We know that R2 equals 20 ohms. So we plug that in for R2. And we know that R3 equals 10 ohms. So we can plug that in for R3. Then we simply add them together and we find out that the total resistance is equal to 45 ohms. 15 plus 20 plus 10 ohms gives us 45. Okay, now we will discuss resistors in parallel. Resistors in parallel are sets of resistors that are not along the same pathway. In order to have resistors in parallel, the circuit must split into two or more distinct pathways. We will find out that when resistors are in parallel, the total resistance is less than the resistance of any of the individual resistors. So now we'll see the current will flow out of the battery from the positive terminal and will follow around the corner. And right when it reaches this junction right here, we will see that the current actually splits between the two pathways. And part of the current follows this pathway up here, and the other part of the current will follow this path down here. Now I'll watch as that happens. The current flows over resistor 1 and resistor 2 at the same exact time before the current meets back up at this junction right here. Then the current continues to flow and connect back together until it returns to the negative terminal of the battery. The formula to calculate resistors in total, the total resistance of resistors in parallel, is given by this formula. Our R total, resistance total, is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth, added together, and then we take the inverse of that value. Now we will look at an example circuit of resistors in parallel. We'll go through this together. First, we need to follow the pathway from the positive terminal of the battery to the negative terminal of the battery. As we leave the battery, we follow the bend and we come to a junction. When we reach this junction, we know that the current must split. Some current will go down and some current will go across the top right here. And so as this current splits, we know that only a small portion of the current is going to go through resistor 1, and the other part of the current will go through resistor 2. And that is how we can recognize a resistor in parallel, is when it goes through two separate paths. So now we simply plug in the values of R1 and R2 into our formula. We find that R1 equals 50 ohms, and we plug that in right here. And R2 also equals 50 ohms, and we'll plug that in right here. So we have 1 divided by 50 plus 1 divided by 50 gives us 2 divided by 50. We will take the reciprocal of that fraction, and we'll get 50 divided by 2, and then we'll get our final answer. Our total equals 25 ohms. Now we will talk about a concept known as effective resistance. Effective resistance is very similar to total resistance. The only difference is that total resistance refers to the resistance of the entire circuit, while effective resistance only applies to a small subset of resistors inside that circuit. It is the equivalent resistance of all of the resistors in a circuit added together. Using the equivalent resistance will help us to simplify complicated circuits by focusing on smaller portions of the circuit. Effective resistance, as we just talked about, is the total resistance of any set of resistors. So in this example, if we look at resistor 2 and resistor 3, we could find out the total resistance of these two resistors simply by adding them together because they're in series. And we will find that their total resistance equals 30 ohms. And so now what we can do is, instead of leaving both of these resistors in the circuit, we can replace them with a single resistor of size 30 ohms. And that's all we've done in the next circuit, is we've replaced the resistor that was down here with the resistor that was up here, because their total resistance together is only 30 ohms. Now you will have the opportunity to do a practice problem. Please pause the video here, and once you have the answer, tune back in and we will go over the solution shortly. Okay, now we're ready for the solution for the practice problem. What we're going to do is the same thing we did with R effective. We are going to see this first set of resistors in parallel, and we're going to solve that first. The math is as such. We just plug it into the formula for resistors in parallel, which is 1 over R1 plus 1 over R2 plus 1 over R3, and then we would take the inverse of that whole thing. Since all of the resistors are 60 ohms, we end up getting 3 over 60, which simplifies down into 20 ohms. So we can essentially replace these three resistors right here with a single resistor that has a resistance of 20 ohms. So now we will move on to the next step in this problem. We're going to now simplify these two resistors, which are in series. And that's very simple to do. We just take the R4 and we add it to our R5, and we get a total resistance, or a resistance effective, of 160 ohms. Notice I'm using a little subscript 2 right here. That's so we don't get confused with our R effective 1 from before. Now as we move on, we'll see that we replaced that resistance with a single resistor of size 160. Now we will carry on, and we will solve for the effective resistance of these two resistors. The effective resistance of those two resistors, because they're in parallel, is given by the formula 1 over R6 plus 1 over R7, everything to the minus 1. And we're not going to go through the math, but it's 5 over 800 to the minus 1, 800 over 5. And then we get our R effective to be 160 ohms. Now, second to last, we have these two resistors that are now in parallel. So we're going to do the same thing as before, and we do our R effective equals 1 over R effective 2 plus 1 over R effective 3 to the minus 1, and that will give us our R effective. And we end up getting a result of about 80 ohms. Last, all we have to do is simplify this circuit. Now, as we'll see, due to the effective resistances, we have a very simple circuit we can solve. It's just 3 resistors in parallel. All we do is we simply add these 3 numbers together to get the total resistance of the entire circuit. R effective plus R effective 4 plus R8 is 20 ohms plus 80 ohms plus 100 ohms to give us a total resistance of 200 ohms for the entire circuit. And that is the solution for this problem. Thank you all for watching, and I hope you enjoyed the video, and I hope it was very helpful to help you understand how to calculate resistors in series and in parallel.